Normal distributions arise frequently in the observation of natural systems, when a quantity is the result of the interaction of a number of random variables. Most of us are familiar with quantities like height or atmospheric temperature being normally distributed, but the normal distribution has a more fundamental mathematical origin. In fact, it's impossible to arrive at the normal distribution just using the random number generator provided in a high-level language. Here's an example of the source we'll be showing today. This is JavaScript source code. I like JavaScript for demonstrating the algorithms because it's built into most browsers and doesn't require a plugin. And browsers now use just-in-time compilers for JavaScript, so execution is very fast. The code starts with some housekeeping that's related to the graphics routines. Further down we can see the code that actually calculates the distribution. Here it is. In order to produce the kind of cool animated effect where the histogram rises from a baseline, process is partitioned into subsets where 100 random numbers are generated and time is allowed to repaint the screen. This is a foreground task, so it can't just keep it running, so it adds a sample of 100 and then reschedules itself for another round if we need to add more samples. This continues until all the samples are exhausted. This routine is called once and starts the sampling process. It also sets the height of the sample or plot in order to the number of samples divided by 6, which was determined experimentally to be an appropriate height. So let's give this a run and see what happens. If we pick a low number like 400, we can see the sampling error is pronounced, and there are significant variations between trials. I'm sure there's a closed form expression that would let us calculate the expectation value of this error as a function of the number of samples, but I haven't done that for this example. If we go up to 1,000 here, you can see we get something that's a little bit more consistent, but we still haven't reached something that looks like a Gaussian or normal curve. When we get to 5,000, we see a Gaussian curve, albeit with some sampling error. And then as we increase the number of iterations up to 10,000 and then 20,000, we start seeing something that's a little bit more consistent. And let's try and there you have it.